Hi, we are Team 21042. We are working with Caterpillar to design a new process to move protective material around CAD's facility.
Hi, I'm Haley Howe and I will be introducing this project. At Caterpillar's facility, the Tucson Proving Grounds, there are many heavy track-type machinery that is driven onto concrete surfaces for testing. To protect the concrete slabs from cracking under the force of the tracks, a conveyor belt material that weighs 650 pounds and is around 40 feet long is rolled out manually by mechanics for the machinery to drive on. The process of laying down this material is time-consuming and costly. It requires 3 mechanics to roll out and roll up this material that takes around 45 minutes. It takes a forklift to transport it around the facility. Because of this, the material is left out in the sun until it has to be moved for upcoming testing. This leaves the material for sun rot. In the new design, there are 3 requirements. First, it needs to reduce the risk of injury for the mechanics who manually move this conveyor belt. Second, it has to have a time-efficient deployment process. Lastly, it has to allow for the material to be stored easily to avoid sun rotting.
Hello, my name is Axel. First off, intro to design. After visiting CAD's facility, our team noticed that the mechanics unrolled the conveyor belt over the concrete surfaces to protect them. Our team started the design by introducing a spool that we allow to roll and unroll the conveyor belt and store it. Since our project focused on minimizing the mechanics' interaction with the conveyor belt, we added a motor to rotate a spool within a frame that will hold up all the material. Then our first design. We started by designing a rectangular spool that is easier to fabricate. As mentioned before, the motor will rotate the spool to reel in and dispense the conveyor belt. After analyzing the design, we encountered a couple of issues. The design had a complicated method to load and unload the spool. Moreover, the operator must control the system while driving the forklift, and a loaded spool could interfere with his sight. Solving these issues led to a second design.
In our second design, we eliminated the electrical motor and replaced that by a drive system that connects the rear wheels to the spool's drive shaft. And now a forklift can push the system to control it. The upper frame now is sliding up and down to pick up the spool from the ground.
Hello, my name is Jonas Stiffy. We have had the privilege of working with Fine Arc Welding for the fabrication of our design. After discussing the second design with them, 3 main problems were discovered. The first is that the time it would take for the fabrication of our design would have either been close to or past the day scheduled for it to be done by. The second is that the cost for fabrication would have been close to $10,000, not including material. The third is the material required for our design would have also been out of the budget, with expensive bearing components and large pieces of solid material that would have been required for the fabrication. As an example, the design of the spool guides had hollow sections in the body to keep it structurally strong for its function. The first approach for the fabrication of this beak from Fine Arc would have been to weld it together. However, with all the tight corners in the hollow sections, the welding would have been difficult and the result would have not been as dimensionally accurate as we wanted it. The second approach would require an expensive piece of solid steel to be cut in a CNC machine for fabrication. This, in addition with a few other problems, would have put the team over our budget of $4,000, so the team knew a redesign was needed.
My name is Ruby O'Brien Metzger, and I am one of the mechanical engineers in this group. Our goal in the third design is to reduce the complexity and to reduce the cost of fabrication. Thus, we went back to our drawing board to simplify the entire system, i.e., we looked at the drive system and the railing system, which raises and lowers the spool.
Hi, I'm Mark Sauer. I've joined the team from Pima College, where I study electromechanical design. Finding ways to reduce the cost of our solution led to 2 major design changes. First, reconsidering the possibility of allowing the spool to roll directly on the ground led to the realization that we could perhaps replace our vertically sliding frame system with a fixed frame. As the viability of that change came into focus, a second major opportunity to simplify emerged. Our drive system was undergoing a costly refinement. A professional consultation had revealed that we needed a clutch to accommodate rotational rate differences between the wheels and the spool. Our gearing system did need the clutch, but the changes we made to the frame gave us a chance to eliminate the power transmission altogether. By changing from a sliding frame to a fixed frame and replacing our power transmission with a direct drive, we got back under budget, created something that's easier to assemble and easier to operate. Our solution now requires 30% less steel, but most importantly, the team believes these cost challenges pushed us to improve the design.
Hello, my name is Chung Kwang Park. To ensure a high-quality product to our customers, our team put together a test plan to test the whole process of retrieving a conveyor belt and moving around. While our team was working on a digital whiteboard, we focused on designing a small system that is strong enough to hold the 700 pounds of the conveyor belt. Our design has 3.7 feet of length and height and 7 feet of width. Since we removed two wheels and add a stand in the back of the system, our new design does not have brakes. Also, we are securing the wheels by wheel chuck to ensure a safe storage of the system. Our design could be operated by multiple forklifts. The forklifts channels are 2.7 feet apart from each other, which is compatible with all forklifts in our customer site. Our rectangular detachable spool should hold the 700 pounds of conveyor belt. We did the finite element analysis with SolidWorks and found that the stress of 3.1 megapascal is applied on our frame due to the weight of the conveyor belt. As the yield strength of the frame is 400 megapascal, our design can hold the weight of 700 pounds.
Hi, my name is Hassan Zain. Our team designed a simple control shaft to connect the drive system with the spool's drive shaft. The control shaft location is accessible to the operator with enough clearance to use it. The shaft lock is on top of the spool guide. It secures the spool in place. Since our system operates at a low speed, we designed a strong drive system to handle high torque and heavy loads. Another interface is the clamping mechanism. Our team uses strong chains that are connected to the spool's frame, with a hook at the end of it to connect it to the conveyor belt via grommet. Although the spooler is big, and it has multiple sub-assemblies, the spooler is a user-friendly tool. To operate the spooler, first load the spool, then connect both the clamping mechanism and the drive system. Finally, use a forklift to push the spooler forward to wheel in or dispense the conveyor belt.
Caterpillar believed that a handling solution for the heavy concrete protection belts at the Tucson Proving Grounds would be a good project for a motivated team of new engineers, and we think our solution proves them right. The spooler we've designed handles the deployment and the retrieval of belts, it reduces the time and manpower required to perform those tasks, and introduces significant safety improvements to the processes. The spooler is simple, robust, easy to maintain, and easy to reproduce. We're excited to see the spooler in regular use, and we already see opportunities to improve it and extend it. We hope you agree. Thank you.